what is it that you need to get started. And so the next few slides are going to be going into the different aspects of the general information that would be helpful to know to get started. In general, anything about your network that you don't already know or have not yet decided on is room for exploration within simulation. However, that's also a huge search space of possibilities, as we kind of just saw, and so you will need to know some things about your network in order to constrain yourself to be able to actually do a proper search of different choices. And so generally, the things that you should have an idea of, at least going in, are and categorize them in these ways. What is it that you're building? What's the network going to look like? What's it actually going to be doing? What do you want it to accomplish? And how's it going to go about doing those things? What processes, what logic is it going to actually use in order to accomplish that task? And if you have an idea of all these, then the last thing you should know is what questions you would like answered still that you can't easily answer without simulation. So let's look at some examples of each of these. Starting with what it is. This is I label this kind of at the hardware level. So this is like understanding in general what the network is going to look like, what its topology is, i.e. its node structure and its link structure, what the distances are generally going to be. Maybe you have a choice in that, but maybe not, right? Oftentimes we have a sort of our nodes and our fibers already in place, and sometimes we have to work with that. If you can have choice, then great. That can be another choice that you can explore in simulation. But oftentimes you'll need to have some basic information about what is where, essentially. And you also need to of course know what's in those nodes and links, what set of hardware you're going to be using, or probably going to be using, at least in terms of like its general types. It's like what sources, what detectors, what quantum memories, if any, what transducers, other optical elements that you might need. Just having a general sense of what it is that you need in your network, and this includes understanding these hardware pieces at hopefully a detailed level. Sometimes you don't need it super detailed. Other times you do. So general understanding, sort of having a good understanding of how this hardware that you're using is characterized is very important. And this can include things like how much optical loss, how much attenuation is in your fiber that you're using. Is there any sort what type of quantum noise is present in a memory, or in the act of transducing? Is there any sort of quantum noise model that is applied to the transduced qubit? Are there any uncertainties in terms of of the timings of things? What is the jitter of a given process? Any other errors? In general, you need to know all the things that can go wrong in your hardware. And so just to maybe make this a little bit more concrete, I've just laid out sort of a high-level example of what it is. So here we can see on the left, a set of nodes and links, and this would be your topology and your distances and stuff. And each of those nodes in this little example, we're imagining that each of these nodes has a quantum memory and a transducer, and we establish entanglement by emitting qubits from memory towards a repeater station, which uses, in this case, a beam splitter and some photon detectors, and maybe other optical elements sometimes. And so in terms of the hardware that you need to know in this case, right, you have in your nodes, you have your memory and your transducers, and the characterization of these hardware might include in your memory, right? Obviously, like how many qubits it has, what are the connectivity of those qubits, i.e. which qubits can interact with each other, what are the decoherence times of these qubits, because we can't store quantum information for very long often. If you're going to be able to do operations on these, what efficiencies do those operations have, and how much time do they take? When we emit a photon, what effect does that have on the emitted photon? But but also, on the qubits that are still left behind. And similarly with the transducer, right? How well does the transducer work, basically? What effective frequencies and bandwidths does it actually act on, and are we making sure to be aligned with those frequencies? And given that, what efficiencies can we actually expect from this transducer? If we send a photon in of one frequency, what is the actual probability that we get a photon out with our transform frequency? In terms of links, similar story, right? We of course have all the optical fibers that are involved with actually moving around the photons, and this can do a lot of different things to them. It can obviously attenuate, i.e. lose photons, and generally we send qubits at a single photon level, and so if we lose that photon, we lose our qubit. And so it's very important to know what the attenuation is that you'll expect from your fibers, and other effects can include what drift does it apply, if any, onto polarization. Is there any sort of jitter that is present in the fiber? Is there any set of dispersion effects that happen that would impact your performance? And within in this case, sort of the mid station itself, what are the efficiencies and other parameters of your beam splitters and detectors and any other optical elements that you have in there. So in general, the more detail you put into these, the more accurate results that you'll get. And it's a little tricky to describe at a high level, like how much detail you need, because sometimes you don't need that much. If you only need sort of a higher level understanding of what your network is going to do. Other times, the pieces of hardware and small little effects can have huge implications, and so it can be sometimes a little tricky to know exactly how much detail you need. But it's a matter of, in general, the more you put in, the better.